So what does it mean if we had this graph? Let's talk about continuity. I know how you all were taught to define continuity. A function is continuous if what? How are you all taught? How do you know if a function is continuous? I mean, go back to the basics. Think about it. If you're trying to prove something is continuous, a graph is continuous, how do you prove it? If you can draw the graph without ever lifting your pen once. If you can put your pen down on a piece of paper, follow the function, and never have to pick it up, that's continuous. That's how most of students were taught to define continuity. A function is continuous. So in this example, which numbers does the function appear to be not continuous? So actually here, what's my domain and what's my range? In this graph, what's my domain? Which axis is the domain? X-axis. So looking at this graph, what's the farthest left, farthest right you can go? 0 to 4. It starts here. Can I use 0? So it's a bracket. Can I use 4? Yes, because there are solid dots at 0 and 4. And everything in between there has points. What's my range? What's the lowest? 0. Can I use 0? No. Because at 0, it's an open circle. How about the highest I can go is 2? Can I use 2? Yes, because they're solid dots. So that's my domain, that's my range. So now, inside this domain, at what points is it not continuous? 1, 2, 4. Very good. Why are those not continuous? I mean, at 1, well, what is f of 1? 1. At this value x, what's my y value? 1. At 2, what's my value there? 2. At 4, what's my value there? 1/2. So even though it doesn't look like it'd be continuous at those points, they exist. But what happens? Why are these not continuous values? Start putting stuff together we learned. Because in this course, if you're going to take Calculus 2 and Calculus 3, you better be able to connect everything you talk about from algebra, trigonometry, Calculus 1, 2, 3, and 4, whatever. You have to be able to connect all these things. Why did you say that 1, 2, and 4, the function is not continuous? I said, yeah, as simplest as it sounds, yes. You have to lift your pencil up, which tells us what? Now let's use the stuff we've been doing already. At 1, why is it not continuous? Using what we know already in mathematics. Does that exist? You said no. Why? Yeah. In order for this to exist, what has to be true? In order for the limit to exist, what has to be true? First, now, is 1 an endpoint or an interior point? It's interior because it's inside the domain. Why do I ask that? Because we just learned, remember the half circle one? If it's an endpoint, what kind of limits can you take there? Only one-sided. If it's an interior point, you should be able to take both sides. So, since this is an interior point, does the limit from the left exist? Where is it going? It's going to 0. Does the limit as x approaches 1 from the right, does that exist? It does, and it's going to 1. The reason it's not continuous is because they are going to different numbers. That's the reason it's not continuous, because as we approach that number 1 from both sides, we approach different values. So what happens at 1? Remember, from 0 to this way, we're going down, 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 down. All of a sudden, what happens when we get close to 1? When we get to 1, what do we have to do? Not go back. Go back means this way. Jump. This is what's called a jump discontinuity. At x equals 1, we have a jump discontinuity. Because it's discontinuous, but from both sides, they approach different values. So, okay, now again, a jump discontinuity is if you're approaching the limit to a value and approaches 2 different numbers. As opposed to 2, what's happening when you get closer to 2? Is it continuous? No, but what's happening there? As we go from x to 2 from the left, what is it approaching? What is the function approaching? 1. Because as we get closer, it's always going to equal 1. What about what's the limit as we approach 2 from the right? We're coming in from the right. Where is it going? It's going to 1. They're both the same, but it's not continuous. Even though both limits approach the same value, what happens at f of 2? What does it become? At 2, what does it become? It becomes 2. We call this so at x equals 2, we have a removable discontinuity. At x equals 2, we have a removable discontinuity. Have we seen this before? Yeah. And then the first example we did in this chapter, we had x minus 1 over x squared plus 1. If you can cancel out those values, the same top and bottom, it's approaching to it, but the value is different. This is called a removable discontinuity. It's different from a jump discontinuity, because a jump discontinuity is, as I draw my graph, it's going down, 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 down. All of a sudden it goes up and over here. Here I go whoop, jump, jump, and but back down. So that's the difference. What happens at 4? Is it a jump or is it a removable discontinuity? That's a tough one, because does it go any further to the right? No, so it just stops there. So it could be the same as this, or it could be the same as this. So that's also a jump discontinuity. Or since it's a single point, you can say it's removable. Until we see the function, we don't know. Yeah, it was a trick question. So right now, because these look the same, at x equals 4, we have a removable discontinuity. Where are the examples? So whenever you look at a function, let's go back to algebra real quick. Jump versus removable discontinuity. What's the difference? How do we know the difference of the two? With what we know so far, without looking at the graph, how do we find a jump discontinuity? How do we find a removable discontinuity? At the endpoints. The endpoints that we're going to hit. Well, you don't have a graph. You just have a function. If I just give you a function, if I give you any function, how do you know if you have a jump discontinuity versus a removable discontinuity? Because okay, if we had the graph, what's the difference between these two graphs? So what does a jump discontinuity look like? What it looks like here is the graph from both sides of x go to different values. A jump discontinuity, you have one graph going this way and one graph going this way. On the left side is continuous, on the right hand is continuous, but they're pointing to the different side. That's how you can tell it's a jump discontinuity. How about the graph of a removable discontinuity? The graph from both sides of X appear to approach the same value, but at f of x, or at that point x, the graph is a single point, not on the original graph. The graph from both sides seem to be approaching the same value, except at that value, it just jumps somewhere else for that one instant, and then it continues the same. Look at the graph looks like. From the left side, it's going here. From the right hand, they're just approaching different numbers from both sides. That's a jump discontinuity. In this one, from both sides, they approach the same number, except at that number, it goes somewhere else for one instant number, and then it continues the rest of the time. So is it continuous at 1? Is the function continuous at 1? No. Well, obviously, you can see that. If I start here, can I draw a line? Can I continue that line? No. So no. How about at 2? Is it continuous? No. Same reason. If I go this way, I have to go here, then I have to go back here. At 4, is it continuous? No, because I have to go here, I got to jump down here. I got to pick up my pen. How about at 3, is it continuous? Yes. So the only point integer are on our graph, only point that's continuous is at 3, because I can go and I can continue the graph without any discontinuity. So removable discontinuities. Removable discontinuities are created when the same value can be removed from both the numerator and denominator. So what's the next example? So what does that mean? If we had a function x squared minus 4 over x plus 2. So I gave you a function. Is this a continuous function? No, it can't be a continuous function because you have a denominator with an x in it. What can you not have in the bottom? The denominator can never equal 0. So what x value will make it equal 0? So we have a discontinuity at x equals -2. Now, is this, so we have a discontinuity because we have a problem there. Is it going to be a jump discontinuity or a removable discontinuity? How do we know that? Because if we take this value, -2, if we put it in the top and the bottom, and we get 0/0, that's a removable discontinuity. Whenever you have 0/0, that means something can be canceled. Something can be removed. So we have x squared minus 4 over x plus 2. The top can get factored at being x plus 2, x minus 2 over x plus 2. We can factor, whenever you have polynomials, always factor them. Can anything cancel? Yeah, this one and this one. Hence, they're removable. So all we have left is x minus 2. This is the graph of our function. Up 1/1. So this is our graph of our function. X minus 2. The y-intercept, slope is 1/1. Except, remember, we had a discontinuity. We had a discontinuity at -2. So take this value, plug it in there. When x is -2, y is negative. So at -2, we have a hole at -4. Because when we take our discontinuity point, where it's our asymptote, where the bottom is 0, plug it into our equation that's remaining, we get our hole, location of our hole. It happens at -2, and the hole appears at -4. So it's going to be a graph, but at -2, -4, there's a hole. That's why it's a removable discontinuity. All right, so let's define these things. We have a series of definitions. Let C be any real number that is either an interior point of an interval or an endpoint of that interval. In the domain of F. This is important. So let's see. C be any point inside the interval. It can be an interior point, or it could be one of the endpoints. That's what we've talked about so far. But it has to be defined on the domain of that function. Everybody got that? So the function f of x is continuous at that c if the limit as x approaches c of that function is equal to f of c. The function is continuous if the function is defined at that value c. The function f of x is right continuous at c if the limit as x approaches c from the right of that function is equal to that value. So it's right continuous if I take the values at c and it's the same value as the function is approaching from the right-hand side. The function f of x is left continuous at c if the limit as x approaches c from the left is equal to f of c. So what do those three actually tell us? What do those three definitions actually tell us? Think about it. If we had a function, f of x, and it's defined on our interval AB, where is C? C can be anywhere. C can equal A, C can equal B, or C can be anywhere in that interval. Now, here's how we define f being continuous with what we just defined up there. It's continuous if whatever value we pick, whatever C we take, that value exists on the graph, no matter where it is. In other words, if the limit exists, we have to check it from both sides. Is it right continuous? Yes. Is it left continuous? Yes. And at the endpoints, if C is equal to A, how can we test it if it's continuous there? How do we test it if it's at an endpoint? Take C from the right. If it's the left endpoint, we have to approach it from the right. If it's the right endpoint, we have to approach it from the left. So this one, if all of these exist, then the function is continuous. That's what it's telling us. So in other words, let's expand this even further. For a function to be continuous at any point in a domain, it has to have the left and right limits existing at each point. For a function to be continuous, every point has to be continuous. If there's one discontinuity, then the function is discontinuous. Here's another example. It sounds easy, but there's work behind it. Example 2. The function f of x equals square root of 4 minus x squared is continuous on -2 to 2. True or false? Is this function continuous on this domain? Mathematically, if I don't show you the graph, first off, remember, it has to be on the domain. What's the domain of this function? So the smallest this can be is 0. So move that over. So we have 4 equals x squared. Square root both sides. Whenever you square root something that's squared, you have to put a plus or minus in front of the answer. So what it tells me is x has to be between -2 and 2. Oh, that's the domain. Are there any values inside there where the function is not continuous, not defined? You could look at it this way. Continuous means defined. We're from -2 to 2. When x is 0, we get +2. So we know that this is a half circle. If it's continuous, that means every value x that I pick, I can plug it inside the function and that value exists. So it has to be defined at those values. Is it continuous? Yes. How do I know? Because inside this domain, I cannot find a value that's going to make it illegal. Can I put 3 in there? Why not? Well, if I didn't have that, can I put 3 in there? No. 3 squared is 9. 4 minus 9 is negative, and you can't take a square root of negative. Because we can't use 3 because it's not in our domain. So again, we can only use the values that are defined in the domain. And so then we look at, are there any values inside here that will make this one undefined? No. So therefore it's continuous at every point. Example 3. The step function u of x below is right continuous at x equals 0, but it is neither left continuous nor continuous at x equals 0. So a step function looks like this. That's what a step function looks like. We're only looking at x equals 0. Is it right continuous? As I come to 0 from the right, why is it right continuous? Why is it right continuous but not left continuous? Why is it right continuous but not left continuous? You won't find it in there, anybody. Here's why. As we're approaching the limit as x approaches 0 from the right of our function, what is the value? What is the limit approaching? As x approaches 0 from the right, where is it approaching? 1. What is the function at 0? At 0, it's 1. Because there's a solid dot right there. That's why it's right continuous. It's coming in from the right, and the value it's approaching and the value it is are the same. Is it left? What is it approaching from the left? It's approaching 0. At 0, what is it? You have your graph in front of you. You have to look at my pictures. So at 0, what is it? Look at your pictures. At f of 0, when x is 0, what's the y value? Calculus students, hello. Okay, draw this picture on your papers because I hate going back and forth, back and forth, back and forth. At x equals 0, what's my number? What's my answer? 1. It's not difficult, not trick questions. It's just basic algebraic observation. Are they the same? No. So that's why it's not left-hand continuous. It's right continuous because the value the graphs approach from the right is the same at that point. And because it's not left and right, it can't be continuous. Test for continuity. So with what we've talked about so far, what are we looking for? What are we looking at to prove if a function is continuous? Three things have to exist. Remember, here's our domain, A and B, and here's C. For it to be continuous, what has to be true? The first thing has to be true is that value at f of C has to exist. So the first thing is the value C. C could be any point inside that domain. Does it exist? The second thing we have to look at, as x approaches C, Does that exist? Now, when I say limit as x approaches c, it exists. What does that mean? For a limit to exist, what does that mean? As the function, as I approach c from both sides, it has to approach a value, and it has to be the same value. So in other words, what we have to look at here is, I'm jumping also a little ahead. For the limit to exist, since we've been talking about it, it has to exist from both sides, and they have to approach the same value. So the function, you plug in the value c, it has to give us a number. You take the limit, it has to approach a number. For it to be continuous, then the limit as x approaches c has to equal that value number. In other words, these two have to be the same values. F of c has to exist, the limit has to exist, and they have to be the same value. That's what it says. Which, let's look at continuity. Is this first one continuous? Why? Yeah, because any value x or c I pick, the limit, the value exists. The limit approaches the same value, and they're equal. So that's continuous. Is this continuous? Why? Because the limit is that. But this value is f of c. Are they equal? No. Here, f of c and L are the same thing. That's how you prove continuity. Is this one continuous? No, because the limit, the left side limit and the right side limit point to different numbers. How about this one? Why? Yeah, f of c is undefined. It doesn't exist anywhere. There is no f of c. So we've looked at some points where it's discontinuous, where it doesn't exist. Discontinuity, where do they exist? How do we know a function is discontinuous? One, if it has a jump discontinuity. What is a jump discontinuity? If it has a removable discontinuity, which means if we plug in a value c, we get 0/0 in the original function. If the function oscillates, what does oscillation mean? If it goes up and down, up and down, up and down very sporadically within a bound, we can't tell what's going on. Well, we know that the sine and cosine function oscillate, but it's gradual as opposed to a very sporadic oscillation. And then we have an indefinite discontinuity. You have an infinite discontinuity whenever you have a vertical asymptote. How do you know if you have a vertical asymptote? The denominator equals 0. You have a, because what happens, for example, the graph 1/x, is that an infinite discontinuity? Can the bottom be equal 0? It's an x. X can be anything. So in this case, whenever the bottom is 0, we have an infinite discontinuity. This graph looks like this. As we get closer, as the limit of 0 from the right of our function, what does it go to? Goes to infinity. Look at the graph. It goes up forever. The limit as x goes to 0 from the left of our function, it goes down, so it goes to negative infinity. Those are indefinite discontinuities, which means we have an asymptote. We have a 0 on the bottom. 1/x², they both go to positive infinity. Again, these are all algebraic. You should know these already. Remind me, next class we'll do the library of functions, because you have to memorize these functions and know what they look like. All right. So let's look at the properties of continuous functions. Theorem 8. Properties of continuous functions. F and G are continuous functions at x equals c, which means it's defined, the limits approaching c give you the same value. The first property, the sum property. I can add, if f and g are both continuous, then the sum of those two functions are also going to be continuous. Again, if f and g are two continuous functions, I could subtract the two functions and it's still going to be continuous. Constant and multiple. If I have some constant multiple in front of my function, remember, if the function is continuous, then I take that continuous function and just multiply it by k, it's still going to be continuous. The product of two functions, f times g. I can multiply two polynomials or two functions. If they're continuous to begin with, their product will be continuous as well. Why is this? Are these obviously true? What would cause it to be discontinuous? What causes a function to be discontinuous? We just talked about it for the last 10 minutes. It has what? Okay, or what do we look for in a function? Well, one, you can look at jump discontinuities. In other words, if at some value c you get 0/0, then it's a jump discontinuity. Or even more simple, if you have a denominator that goes to 0. But if you have a function that has a denominator, is that a continuous function? No, because the bottom can go to 0. All of these functions are continuous. They have no vertical asymptotes, no horizontal asymptote. They're just continuous functions, like polynomials. Quotient. F over G. Only if the function on the bottom does not equal 0. And we have a power function. If your function is continuous and you just take an exponent to it, of course it's going to be continuous again because of the product rule. F squared will be f times f. If f is continuous, then f times f is continuous. Or roots, which means we have radicals. If you have a continuous function and you take the radical of it, of course it's going to be continuous also. Example 7. Let's do number 6 first. If we had some polynomial, this is a sub n, a n minus 1, x n minus 1. If you have some polynomial and it's continuous at every value c, just plug it in there. All this says here is if you have a polynomial, we know polynomials are continuous. unless they're rational expressions. Then just plug the value in there. We're done. How about if f of x equals the absolute value of x? Is it continuous at 0? Can we take it at 0? What's the absolute value of 0? Is that in the domain? What's the domain of absolute values? All real numbers. Is that in the all real numbers? So it's continuous. How about inverse functions? Do you remember how to find inverse functions? A function has an inverse if and only if it is 1-to-1. A function has an inverse if and only if the function is 1-to-1. In other words, for each value of x, there's one and only one value of y. What that says, for every x, there is one and only one value of y. That's what 1-to-1 means. If that's the case, remember, if the function has an inverse, it has to be 1-to-1. So if f of x is continuous, then the inverse is also continuous. Don't believe me? If f of x equals x squared, what's the inverse function of x squared? Square root of x. So that's continuous. Each x only has one value of y, so therefore the inverse is also continuous. Exponential functions. The inverse of an exponential function, it's a natural log. If this function is continuous, then its inverse has to be continuous. Yeah, we have a few more pages. We'll pick up from here next time. We'll look at, so we know inverses are because they're 1-to-1 to begin with. Next, we're going to look at composite functions. What are composite functions? Functions within functions. What we're saying there is if g of x is continuous, and we plug it inside f of x, and it's continuous, then the composite function that results is also continuous. Because there are no values that are asymptotic. But we'll look at that next time. Questions?
Oh, yeah. And what was that?
Example 6. Example 6 simply said, if we had a polynomial, any polynomial, and if the value at any value c inside the domain, just take it and plug it in there. If it's a continuous function, then the value will exist. So if the function is continuous, then we just take the limit, throw it in there. You're welcome. So next time we're doing composite functions and a whole bunch of examples from there.